Hello everyone, I'm Baoxiang from Xi'an Jiaotong University. Today I'm going to talk about achieving high quality of attribution in provenance-based intrusion detection systems. In recent years, to deal with the threat of cyber attacks, system provenance has become a popular technique for intrusion detection. System provenance records the interactions between system objects, which is also called system events, and it represents system behaviors as a directed, attributed, and dynamic graph called the provenance graph. When there is a cyber attack, the abnormal system behaviors result in an abnormal provenance graph structure. To detect the cyber attacks in the provenance graph, the PIDS was proposed. A major category of PIDS is the anomaly-based PIDS, which is trained to learn normal graph structures and identify abnormal graph patterns as malicious. Due to the potential to detect advanced cyber attacks, there are many anomaly-based systems already being applied in intrusion detections. However, current systems always report attack signals with low attribution quality, providing overwhelmingly large amount of contextual information, which results in a lot of fatigue and frequent burnout. We identify two main factors leading to this limitation: data imbalance and improper evaluation strategies. The first factor is data imbalance. In a provenance graph, the prevalence of malicious nodes is very small, so it is difficult to precisely identify them from the graph. Another factor is that current works apply improper evaluation strategies. Given an attack node, they consider all nodes that are in the neighborhood, in the same batch, or have the same source node as malicious. As shown in the table, those strategies overestimate the number of malicious nodes, leading to high false positive rates. In our work, we open source a ground truth without any evaluation strategy. Only attack-related nodes are considered as malicious. To address the limitation mentioned above, we propose ORTHRUS, a PIDS providing high-quality attack signals. Here is the overall workflow. First, it collects system provenance and builds provenance graph. Then edges are featurized into feature vectors. Third, an encoder-decoder architecture is used to learn temporal and spatial information from the graph. Then the automatic thresholding is conducted to detect anomalies. Finally, it reconstructs the attack, starting from anomaly nodes. When building a provenance graph, nodes stand for system objects and edges stand for events, and the edge direction follows the direction of data flow. The edges are featurized into vectors. ORTHRUS first encodes the attributes of nodes. Node attributes are tokenized into sentences, and then each word is embedded using a word-to-vec model. Then the node embedding is average word embeddings. An edge vector consists of node embeddings and one-hot node types and edge types. ORTHRUS then use an encoder-decoder architecture to learn the temporal and spatial information from the vectorized provenance graph. A Jiang-based encoder learns to generate edge embeddings. Then the decoder predicts edge types from the embeddings. The reconstruction errors are calculated as a loss of the model and used for backpropagation. In the encoder, ORTHRUS samples a most recent event for each edge. Then an attention-based GNN model is used to aggregate information from sampled neighbors to the target node and generate an embedding for the target node. Attention coefficients are calculated between the target node and each sampled neighbor, which is used as the weight of information aggregation. The attention mechanism allows each node to focus on the most relevant neighboring information. The decoder predicts edge types based on the embeddings of the end node. And the reconstruction error is set as the cross-entropy loss across edge types to predictions. By optimizing this loss, the model is forced to learn temporal and spatial patterns of normal behaviors. During detection, abnormal events lead to high reconstruction error, which is assigned to the end nodes and used for anomaly detection. Before training, a batch of benign data is reserved as the validation set. ORTHRUS calculate the highest loss in the validation set at the threshold. It indicates the largest anomaly score deviation among benign activities. Then a k-means model is used to divide all nodes with a score higher than the threshold into two clusters. The cluster with a higher anomaly score is reported as true malicious, and the other cluster is filtered out as benign anomalies. The last step of ORTHRUS is to reconstruct the attack from detected anomalies. ORTHRUS conducts causality analysis to identify potential entry nodes and the exit node of the attack. The entry node stands for the root cause of the attack, while the exit node stands for the final impact. The subgraph between an entry or exit node and the anomaly node is defined as a dependency graph. ORTHRUS calculates the critical scores for each dependency graph and identify the most critical one as the reconstruction of the attack. We conducted a comprehensive evaluation to answer these research questions. And we use benchmark datasets published by DARPA-TC programs. We take 5 most recent anomaly-based PIDs to compare with our system. Here is the attack level result, which shows that ORTHRUS can detect all attacks in the public datasets. Here is the node level result. ORTHRUS reports true positives with only a few false positives and gets the best precision, while other systems report either no true positives or a large number of false positives. This indicates ORTHRUS provides attack signals with higher attribution quality. These figures show the anomaly scores calculated by graph learning models of different systems. ORTHRUS differentiates malicious and benign nodes with a larger margin. This indicates that the better performance of ORTHRUS comes from the better learning capability of the model. And the results show that, in most cases, ORTHRUS gets the best computational efficiency. Here, the figures shows the results with different hyperparameters. Note the orange line. ORTHRUS can detect all attacks in most cases, even if the parameter changes a lot. The results demonstrate the robustness of ORTHRUS. We conducted the ablation study on 2 datasets. As shown by the results, different components have different effects on the precision and computational efficiency. All components contribute to the overall performance. As a summary, we discussed the factors leading to low attribution quality and proposed a solution. And then we conducted a comprehensive evaluation, and we open-sourced our system with a solid ground truth without any improper evaluation strategies. That's all. Thanks for listening.